Welcome to the Marine Waters Long-Term Monitoring Program. I'm Christopher Krembs. I'm with the Washington State Department of Ecology, the Environmental Assessment Program, and I work in the Marine Monitoring Unit. I'm a member of a team of 9, and it is because of the hard work and the contribution and dedication of that team that we now have a long-term data set of the environment that allows us to look at long-term trends in water quality in Puget Sound. So what are we doing in more detail? We're looking at the trends in eutrophication and dissolved oxygen over long time periods, and we have a network of long-term monitoring stations that we've been entertaining since 1973, indicated on this figure. I would like to point out that we have also 3 near-ocean reference stations in the Strait of Juan de Fuca. I'm going to come back to that, so I would like to point that out. The backbone of our operation is a seaplane. We've been visiting the stations by this plane monthly, and in the hull of the plane we have an opening so we can lower a sensor package and also Niskin bottles into the water column, and we take full vertical profiles. Lately, we also augmented our efforts with an en route ferry system, the Victoria Clipper, as you can see here. And we have fixed moorings in strategic locations and also use satellite imagery to sort of look at the larger pattern and how everything sort of fits together on a larger geographical scale. So we collect a suite of environmental variables that is not only sort of geared at water quality, but also allows us to understand estuarine processes on large-scale fluctuations in the marine system. And first of all, I would like to sort of step back and take you at a little distance to Puget Sound. You see Puget Sound here on the satellite image. This is a remote sensing image on chlorophyll. Colors indicate higher chlorophyll concentrations, and you see the strong upwelling system that we have off the coast of Washington. So Puget Sound is connected through the Straits of Juan de Fuca to a strong upwelling system. And upwelling systems are characterized by bringing nutrient-rich water that also can be low in oxygen to the surface, in particular during the summer months. There are 2 indicators or indices in the literature that allow us to sort of place large-scale oceanic variability into sort of a context of water quality in Puget Sound. One is called the Pacific Decadal Oscillation, looking at sea surface temperature variability over time. And the other one is the Upwelling Index, provided by the Pacific Fisheries Environmental Laboratory in blue. And so on the figure below, you have sort of a context of 70 years of these indices over time. Positive values indicate in red warmer temperatures than expected, in blue sort of stronger upwelling than expected in that region. And so normally they are exclusive of one another. That means that if you have warmer sea surface temperature, you tend to have less upwelling. But there are also times here from 1999 on to present where the 2 indices indicate that upwelling and sea surface temperature begin to be sort of more in phase with one another. And I would like to draw your attention to the year 2008, because we had a significant decrease in upwelling activity in that year. We collect an entire suite of water quality indicators, and I would like to show you the indicators in a similar anomaly space. And what we do is we take a time average seasonal cycle and subtract that from our measurements, and we're left basically with the anomalies. And schematically, you can see this on the figure that red indicates measurements that are higher than expected, green lower than expected, black are measurements that fall basically into the sort of average expectation for a particular indicator for a particular site and season. So if you take that and flip that on its head, we use, you can generate a heat map, and each box represents a sampling event. Colors indicate anomalies, black expected values, and gray indicate sampling events that we missed due to weather. And you can sort of list that for an entire sort of station network, and I would like to show you an example of this on the lower figure here, where you can see the thermal energy content from 0 to 50 meters in the water column. So that is basically temperature. And just subjectively, you see a shift from green to red in the middle of the last decade, from 2003 to 2006, and then a shift to green again. And that shift sort of permeates the entire Puget Sound region. So it's a huge signal. And when you look at the sea surface temperature anomalies in the Pacific, you see that these two patterns nicely coincide. So if you take now an average over the entire Puget Sound region over 12 months and look sort of at it on a larger scale, as I've done here with one data point, you can correlate the thermal energy content with the sea surface temperature variability. And you see a nice correlation between the two. So what that means is that you cannot look at Puget Sound and its water quality in isolation from large-scale Pacific processes and variability. We are particularly interested in oxygen as a stress indicator to nutrient enrichment in Puget Sound. And what I would like to show you are data where we not look only at the concentration of oxygen, but we look at an entire deficit in the water column. And I would like to explain that with a schematic drawing here. So if we get a vertical profile of oxygen with depth here in red, we also get values in temperature, salinity, and pressure, which allows us to calculate a theoretical 100% saturation line for oxygen. So if you take that area, indicated here in black, and integrate that up, you arrive at an oxygen deficit. And we look at that variability again of that deficit over time. And when you do that, as indicated in this lower heat map for all the stations, you see again a shift from green to red over time. And then in 2010, on the other side of the graph, you see that it begins to erode away. And if you look at the upper graph and look at the upwelling index, you see that these patterns nicely match. So we look at the depth bin 20 to 50 meters to be away from the euphotic zone, because sort of primary productivity can affect the signal. And take again an average over the entire Puget Sound region, and we see that we have an increase in the deficit up to 2006, and then it begins to erode away and slowly begins to decline over time into the present time. To show you that also the water column 50 meters to deeper is affected, I plotted the data that we have from the time period 2002 to current in small red dots, and you see that these trends nicely sort of reflect one another, indicating that 20 to 50 meters is also representative of deeper water. So if you correlate now the variability and the oxygen deficit with the upwelling index, you find a significant correlation. Even though the correlation is weak and there's quite some noise in it, it indicates that the ocean plays a very important role. So the question is now, is the ocean the only one to blame for the DO deficit? And I would like to show you that this is not the case. And in order to do that, I would like to show you the trends in nitrate over time. Again, you see a shift from green to red over the 12-year period. And if you take again sort of a yearly average, Puget Sound average, in that anomaly, you see a significant increase over time. And that increase is 3 micromoles per 10 years. It appears like a small number, but bear in mind that this is what is left over after the organisms have taken out the nutrients already that they needed. And so nutrient increases can spur large phytoplankton blooms that we also see in Puget Sound, as indicated on the picture up here. Phosphate is also increasing, sort of same projection. You see a significant increase over time. However, the increase is 1 order of magnitude lower than that of phosphate, just indicating again sort of how sensitive our approach is by removing a seasonal signal. Okay, so what indications do we now have that this is a source that is potentially non-oceanic? Silicate and dissolved inorganic nitrogen, meaning sort of nitrate, nitrite, and ammonia, tend to be in a constant or fairly stable ratio in the oceanic environment. So if you see a shift in that ratio of silicate to dissolved inorganic nitrogen, you have an indication that you have non-oceanic nitrogen sources shifting that ratio. So when we look at that ratio in the Puget Sound region, we see a significant decline over the last 10 years as well, which is about 10 units. So that's a significant decrease, which is strongly indicative that the ocean does not play a large role in that increase that we detected. We also have a second indication. Remember, I pointed out the near-oceanic reference stations in the Strait of Juan de Fuca. At these stations, we also take nutrient and salt salinity measurements, and we can use salt as a passive tracer for the oceanic influence. And so when we take the nutrient to salt ratio in the Straits of Juan de Fuca, we can remove the oceanic variability from our data set using basically the model of a simple dilution line indicated by the formula in the lower left box. So if we remove that oceanic signal, we'll still see a significant increase in nitrate and phosphate over time, providing a second line of evidence that that increase in nitrate that we saw is due to non-oceanic sources. Okay, so how do we now stitch together an increase in nutrients and increase in the oxygen deficit, or basically the interplay between the two? Well, in oceanography, you can have primary productivity in the surface layer where you have enough light, and typically nutrients are provided by upwelling of these nutrients to the surface layer or mixing into the surface layer. There are two forms of productivity in the upper mixed layer, in the euphotic zone. One is regenerated production, meaning that phytoplankton take nutrients up through photosynthesis, produce organic material, then ultimately die, get remineralized, and the nutrients are taken up by other phytoplankton just in their vicinity. There's, however, also export production, meaning that whatever is produced in form of organic material can now sort of sink to a deeper water column, and is remineralized by microbes at depth. And that process of remineralization by microbes is heterotrophic, meaning that it requires oxygen, and that drives the oxygen deficit up in the water column. So it is truly the export production that is connecting a nutrient enrichment with the oxygen deficit at depth. And in oceanography, there's a classical concept in that nutrients are sort of brought into the upper layer, and typically in the oceanic environment, they're in the form of nitrate. So if you take the ratio of nitrate to total dissolved inorganic nitrogen, including nitrate, nitrite, and ammonia, then you get sort of a fingerprint for upwelling in the system. And so if we do that, again, Puget Sound wide, and we look at the change in the nitrogen ratio and correlate that with the change in the DO deficit, you see sort of a positive correlation between the two. That implies that when you have upwelling and mixing of nutrients into the upper water, you will have more organic material export and therefore promote the oxygen drawdown at depth. So that basically confirms an oceanic concept very nicely even for Puget Sound. So what does that mean for water quality? Well, I showed you that the ocean plays an important role in driving the oxygen deficit. So we cannot really look at water quality in isolation of large-scale oceanic processes, in particular upwelling that we have along the coast. And we found that despite a sizable oceanic influence on the DO deficit, macronutrients tend to increase over time, which is sort of based on nutrient ratio, much more indicative of eutrophication and potentially a human contribution, but not for sure. And then I showed you on the last slide that the DO deficit also responds strongly to qualitative changes in the nitrogen sources, which is more indicative of upwelling and mixing. So taking these three natural components that compete and interact with one another and superimposing a human signal on top of that, it's very hard sort of to find who the culprit really is for a particular increase in the DO deficit over time. And in order to sort of approach this more effectively, the environmental assessment program strategy is to use modeling as a quantitative solution to evaluate the impact of a human contribution to the DO deficit. And the data that we produce in the long-term marine water monitoring program supports these efforts on sort of a larger scale within ecology.